So this video is going to focus on a factoring review. So whenever we approach factoring, there's all sorts of different techniques for factoring. But before we get to those techniques, one of the things that we're supposed to be looking out for first is, does it have a greatest common factor? If we have a greatest common factor, we want to definitely factor that out first, then take a look at what we're left with to see if we can factor it further or not. So when we are looking for a greatest common factor, there's some things that we want to pay attention to. First off, if our leading term here, so the term with the highest exponent, right, if it is negative, right, you don't want a negative out here in front as your leading coefficient here. So if that first term there is negative, you definitely want that negative to be factored out part of your GCF. So we are going to pull that negative out. The next thing you want to look at is your numbers. And here we have a 9, an 18, and a 27. Now, you want to see what is the biggest number that you can pull out from each one of these numbers. Now, you need to start with your smaller number because I can't have my GCF for my numbers cannot be bigger than 9, right? Because I only have 9 here. I don't have 10 to take or 11 to take. I only have 9, right? So think about what goes into 9, what goes into 18, and what goes into 27. Now, for this one, you should be thinking 9. Like, pretend if this were a big fraction, 9 over 18 over 27, what could you divide out from each one of those numbers? So it's definitely a 9. 9 divided by 9 is 1, divided by 18 is 2, divided by 27 is 3, right? So they're all divisible. Then pay attention to your variables. You want to make sure that each one of your terms has that variable. So we have 1, 2, 3 terms. They each have an x. As long as they all have an x in it, you want to take the lowest exponent out of them. So the lowest power. So this one has x to the fourth, x cubed, x squared. 2 is the smaller of the numbers, so you're going to take x squared. So our GCF for this problem is a negative 9x squared. We're going to factor that out. So we're going to factor it out, pull it out to the front of the problem. And to see what's left over when we do that, we need to divide our problem here by our GCF, the negative 9x squared. So we need to divide it out of each term. When we divide, negative over negative cancels, 9 over 9 cancels, and when we divide x over fourth to x squared, remember you subtract exponents. Drop down the x, 4 minus 2 is a 2. Move on to your next division. Negative over negative is a positive, 18 over 9 is a 2, and drop down your x, 3 minus 2 is a 1, which we don't need to write. Last division, different signs makes that a negative. 27 over 9 is a 3, and x squared over x squared cancels, right? We have a 2 minus 2, which is a 0. So we do need to take a look at our remaining polynomial here and see inside our parentheses, can we factor this further? And we can definitely factor this further here. I'm going to drop down that negative 9x squared. And here I'm going to take a look at this trinomial. And we're going to focus on factoring a trinomial where your leading coefficient is a 1. So the first thing I'm going to do is draw my parentheses. And when it comes to factoring trinomials with the leading coefficient of 1, remember, the first spots in these parentheses need to multiply to get the first spot here in this trinomial. The last spots in the parentheses need to multiply to get the last spot here in this trinomial. So we need to think what times what gets us x squared. Well, the only thing that's going to get us x squared is an x times an x. X times x is x squared. Then we're going to skip over the middle here. We need to focus on the last. What times what multiplies to get a 3? Well, the only way you're going to get a 3 is a 1 times a 3, right? So one of the last things we need to focus on with the factoring here, and again, this is a factoring review. If you need a little bit more detail on this, I would watch one of my factoring trinomial videos. But otherwise, if your last number is negative, these are going to have different signs in between. One's going to be a plus, one's going to be a minus. The way that you know which is which, look at your middle term. Whatever sign the middle term has, it needs to go with the bigger out of these two numbers. So since the middle term is a plus, and 3 is bigger than 1, the plus is going to go with the 3. And since we said they have to have different signs, I'm going to put the minus over there. This is our fully factored example. The great thing about factoring is you can check your work, multiply this all back out, and you should get your original expression there. Moving on to the next example. Anytime you approach factoring out the greatest common factor, one of the first things you do want to pay attention to is how many terms do you have in the problem. In this particular problem here, we have two terms, 1, 2. Right, they're separated by this plus sign here. So we're comparing this and we're comparing this. Now when we compare these two, I see I have an x squared here, but I don't have an x over here. I have a 17, but I don't have any numbers here in front to compare it to. So I actually don't have anything in common with my numbers and variables like I did on this side here. But I do see that I have a 2x plus 5 here and a 2x plus 5 here. And I can factor that out to the front. When I factor out 2x plus 5, it's going to work just like over here. We're factoring it out to the front of the problem, and we're going to divide it out of each term to see what we're left with. When we look at this first division here, keep in mind if you have the same thing over the same thing, it is equal to a 1. So like 10 divided by 10 is a 1. X divided by x is a 1. 2x plus 5 over 2x plus 5 is a 1. And x squared times 1 is just x squared. That's what we have left over. Drop down this plus sign in between and do the next division. Same thing's going to happen here. 2x plus 5 over 2x plus 5 cancels to a 1. And 17 times 1 is just a 17. So drop that down, wrap that in parentheses, and we are done with our factoring there. Now, for factor by grouping, that's going to be the next factoring technique we're going to talk about. It's essentially a 4-step process. The way that we know that we are definitely using factor by grouping and not any other technique is the fact that you're going to have 4 terms in each one of your problems. So 1, 2, 3, 4, 1, 2, 3, 4. That's typically our sign initially that we are using this technique. First step in this technique, you're going to chop your problem in half, cut it right down the middle. All right, so typically when we approach a factoring problem, we check to see if we have a greatest common factor. But we don't have a greatest common factor amongst all of this. These 3 have an x, but this one doesn't. 4 and 12 have something in common, but 3 doesn't go into 4, or 3 and 12 have something in common, but the other 2 don't. So I can't make anything work. So what we do is we chop the problem in half, and we're going to factor out a GCF from each one of these groupings. We're going to pretend that this is separate. We're going to treat them as different problems. When we're looking at our first grouping and looking for a GCF here, I don't have a number here. I have one here, so I can't pull out a number with my GCF. But they each do have an x. Out of x cubed and x squared is the smallest. So x squared is going to be my GCF. I'm going to pull that out to the front, divide it out of my problem to see what I'm left with. When we divide this, x cubed over x squared is an x. Drop down your minus sign, and dividing here, x squared over x squared is going to cancel to a 1, which means we're just going to drop down that 3. Then we're going to pretend that this is its own separate problem over here and do the same thing. Factor out a GCF from this. If I'm looking at a 4x and a 12, well, 4 and a 12 has a 4 in common, and that is a positive 4 that they would have in common. This one has an x, this one doesn't, so I can't pull out an x with my GCF. So it looks like it's just going to be a positive 4. Again, factor it out to the front, divide it from that part of your problem here to see what we're left with. 4 over 4 cancels to a 1, so drop down the x. Minus 12 over 4 is a 3. Now, anytime we do factor by grouping, what we're looking for here is we are looking to get the same exact factor inside the parentheses. So we can see I now have 2 terms in my problem. Right, I started with 4, I turned this into a 2-term problem. But if you notice here, inside the parentheses, we have the same exact thing. This is just like this problem up here. We had the 2x plus 5s in common, so we're now going to factor that common factor out. So we're going to take the x minus 3, right? We have one here, we have one here. Pull that out to the front as your GCF. Divide it by both of these terms. When we do so, the x minus 3s are going to cancel. X minus 3 cancels with x minus 3, you get a 1. And again, x squared times 1 is just an x squared. Drop down the plus sign that was here in between and do the next division. X minus 3 over x minus 3 cancels to a 1. Again, 4 times 1 is just a 4. Wrap that in parentheses, and that is your problem all factored out. So let's try that one more time. And factor by grouping, You have 1, 2, 3, 4 terms in it. Step 1, chop it in half, factor out a GCF from each grouping. Looking at my first grouping here, again, no numbers. They each have x's. Out of 3 and 2, x squared is the GCF. Pull that out to the front, factor it out of your problem. When we factor that out, which means we're dividing it out, again, x cubed over x squared is an x, minus x squared over x squared cancels to a 1 since there's nothing else there. Looking at our back grouping, again, we do treat this as if it's its own problem. So we do see here we have a negative in front. Remember that rule. If your leading coefficient, if your leading term is negative, you must factor out a negative with your GCF. Otherwise, 5x and 5 has a 5 in common. So here our GCF is going to be a negative 5, and that's what we're factoring out. When we factor that out and divide, negative over negative cancels. 5 over 5 cancels, leaving us with the x. Different signs here makes that a minus, and 5 over 5 is a 1. Again, the whole point is to get the same factor inside the parentheses. If you get different things, go back up, check your work, you made a mistake. The point of this technique is to get the same exact factor inside these parentheses. Every once in a while, you might need to rearrange a term or two in order to make this happen. Now, once again, we're left in the same situation. We have a common factor here. We're going to pull out that x minus 1, which means we're going to divide it out from each one of our terms. The x minus 1s are going to cancel. And if you notice here, we're just going to be left with the x squared here in front, since those cancel, minus this 5, since these cancel. And there is our solution. All right, so now we're going to move on to factoring trinomials, starting with factoring a trinomial with the leading coefficient of a 1. We did do this in the first example on the last page. So anytime you approach a factoring trinomials problem, one of the first things you want to look for, do we have a GCF? Now we don't in this one. We don't have an x in all three. We don't have numbers in all three that we have in common. Again, a 1 does not count. So we can go straight to drawing our parentheses to factor. Always start by looking at the first term. And you, again, the first positions here must multiply to get this first term. We know that an x times an x is an x squared. So then we focus on these back positions here, because this times this has to get us our 45. Now, I always make a small list, whether I make it in my head or I write it down, of everything that multiplies to get 45. 1 times 45. 2 doesn't go into 45, but 3 does go in 15 times. 4 doesn't go in. 5 times 9 is a 45. So these are all the different combinations of things that multiply to get 45. What we want is what multiplies to get 45, but what adds to get, or adds or subtracts to get a 14. Now, the way that we're going to get a 14 here is by using that 5 and that 9, since 5 plus 9 is a 14. So I'm going to put in the 5, I'm going to put in the 9. Doesn't matter which one goes where. What's most important is what signs go in front of them. If your back number is positive, these are going to have the same sign, either both pluses, both minuses. Your middle term is always key. If the middle term is negative, they're both going to be negative. So x minus 5 times x minus 9 is how this factors. Again, you can always check your work by multiplying this back out and seeing if you get the original problem. Moving on to the next one. All right, taking a look at this trinomial here, we want to see, do we have a greatest common factor? We don't have an x in all three. 3 does go in, well, actually, no, 3 does not go into 25. 3 does not go into 28, so there is no GCF here. So we're going to be factoring a trinomial that has a leading coefficient that is not a 1. For these problems, I use a technique called no fuss. So the way that no fuss works, take the first term, ignoring the exponent, write it down twice. 3x, 3x. Step 2, take your first number times your last number. 3 times 28. That is an 84. So you want to think everything that multiplies to get an 84 that adds or subtracts to get a 25. Well, it's actually the 3 and the 28, because 3 times 28 is that 84, and 28 minus 3 is a 25. So we're actually just going to use the 3 and the 28. Step 3, look at your signs. If the back number is negative, these have to have different signs. Again, remember, middle term is always key. Whatever sign the middle term has, it must go with a bigger number. So the minus has to go with the 28, plus has to go with the 3. Last step in factoring using no fuss, you need to reduce one or both of your factors. So think of this as a fraction. Here I have a 3, here I have a 3, which means I can divide out a 3. And when I do so, I'm left with x plus 1 here. Looking at this back factor, I can also divide by, I'm sorry, no I can't. Brain fart moment here, right? 3 does not go into 28, so we just drop this down, leaving it 3x minus 28. So this is our final answer. That last step in no fuss, always one of these will be able to be factored. Sometimes both, but at least one of these should be able to be reduced. I'm sorry, I think I said factored. But you should always be able to reduce one of these in the end. All right, moving on to our next example here. So we're still working with trinomials. And again, typically when we approach a problem, we do want to check to see if it does have a GCF. We don't here. Nothing in common with the 3, 4, and a 1. These have x's, but this one doesn't. These have y's, but this one doesn't. So we are going to go straight to drawing our parentheses. I'm still going to use no fuss factoring in order to factor this. So I'm going to look at my first parts here, right? First part of my parentheses, need to multiply to get that. So we do have the x times x, or again, in no fuss, you're going to repeat this twice. 3x times 3x. But when we go to our back term, notice that we also have a y squared here. Typically, we just have a number in that back position, but we have a variable here. So just like x times x is x squared, we know y times y is going to give us a y squared here. Otherwise, focusing on our numbers here. All right, so step 1 of no fuss was to take the first term, ignoring the exponent, write it twice. Step 2, multiply the first number times the last, which is a 3 times a 1, which is just a 3. All right, so that means we're, in order to get this 3, we're going to put a 1 here, we're going to put a 3 there. Everything is positive here, so everything is going to be positive here. Last step in no fuss, reduce one or both of these factors. Nothing in common between a 3 and a 1, and I actually don't need to write this 1 here. It is understood. So that is just going to be 3x plus y. This one over here, we can reduce it by a factor of a 3, so we're going to divide that by a 3, leaving us with an x plus a y. And that would be our final answer there. Moving on to our last trinomial example here. We have no GCF in this example. We are going to go straight to our parentheses using no fuss once again. Take your first term here, ignoring your exponent, write it down twice. Step 2, multiply the first number times the last number. 9 times 1 is a 9, and the only way to get a 9 is that 1 times 9, or 3 times 3. But remember, you want what's going to add or subtract to get your middle term. Here we have a 6, which means we are going to be using the 3 and the 3. Focusing on your signs. If your last term here is positive, they're going to have the same sign. Look at your middle term. It's going to let you know which one. So these are both going to be minuses. Last step in no fuss, reduce, reduce, reduce. So I'm going to be able to divide a 3 out from all of this here, right? Because 3 goes into a 3 and a 9. And notice these are the same exact factor here. 9x minus 3, 9x minus 3. So I can reduce it all by a 3, which is going to give me a 3x minus 1 times a 3x minus 1. And since we got the same factor for each one of those, we can go ahead and group these together and call that 3x minus 1 squared. The last thing we're going to talk about is different special factoring techniques, difference of squares, difference of cubes, sum of cubes, things like that. So, starting with difference of squares. Now, we know that we're using difference of squares, and I have the formula for it down over here. And these special factoring techniques do require a formula in order to factor them. We know we're using difference of squares because of 3 criteria. First off, you have 2 terms. Second thing, they have to have different signs. One's going to be positive, one's going to be negative. Third thing is they must both be perfect cubes. So when perfect squares. which means that the same factor times the same factor can multiply to get it. So like, for example, 100 is a perfect square because 10 times 10 gets you that. 15 would not be a perfect square. 3 times 5 gets you 15, but 3 and 5 are not the same thing, right? 10 and 10 are the same thing, and they multiply to get 100. So that's what we're talking about with the perfect square. Now, in order to use the difference of squares formula, so this is how it works, right? You're going to start off with your a squared minus your b squared. So that's this part of the problem. It's going to factor to a plus b, a minus b. So we need to know what is a, what is b. Well, a is, if you take a look at your first term here, what times what gets you 9x squared? You can also think about it, what is the square root of 9x squared? Well, the square root of 9 is a 3, and the square root of x squared is an x. But also, 3x times 3x is 9x squared. B is just going to be what times what is 25y squared, or what is the square root of 25y squared? Well, the square root of 25 is a 5, and the square root of y squared is a y. 5 times 5, or 5y times 5y is 25y squared. This is the hardest part of the problem. Once you know what a and b are according to our formula, add them together, right? 3x plus 5y. Subtract them together, 3x minus 5y. That is your answer. Let's try another one. This is also difference of squares. Now, this is difference of squares. I do have two terms. They do have different signs. This is positive, this is negative. They both are perfect squares, because if we look at x to the fourth, well, x squared times x squared is x to the fourth. If we look at our second term, 1 times 1 is 1. Add them together, subtract them together. Now, this is not the final answer. Maybe pause the video for a little bit, take a look at this problem, see if you can figure out why this is not the final answer. But I'm going to let you know here, this is not the final answer because x squared minus 1 can be factored further. If we take a look at this, this is also difference of squares. The first one isn't. I have two terms. They do not have different signs. They are both positive. So this one is just going to drop down. But x squared minus 1 is difference of squares. Again, two terms, different signs. One's positive, one's negative. And they are both perfect squares because x times x is x squared and 1 times 1 is 1. So this would factor to x plus 1, x minus 1. So slightly tricky right there. This is your final answer. Okay. So let's move on to the difference of cubes and the sum of cubes. So over here, we're going to start with the sum of cubes. We know it's the sum of cubes, well, because we have two terms. There's a plus sign in between them, and these are both perfect cubes. Now, for the formula for sum of cubes is down over here. Maybe pause the video and get these written down. Again, these are in order, difference of squares, sum of cubes, difference of cubes. Otherwise, we also have to assign an A and a B for these. We have to follow the formula. Because we're dealing with cubes, again, cubes is 3 multiplications. What times what times what, right? 3 multiplications to get that. So A is what times what is x cubed? Well, x times x is x cubed. Then we look at the 27. What times what is 27? Well, 3 times 3 times 3. So, according to our formula, and let me just go ahead and write it up here so I have it to reference to. And this is exactly what we need to plug into. So we're going to have a binomial followed by a trinomial. Our binomial is going to be a plus the b, x plus the 3, right? A plus b. Our trinomial, take a, square it. A is an x, and if we square this, x times x is x squared. Then it says minus. So minus a times b. X times 3, 3 times x is 3x. Then take b and square it. I'm sorry, that's supposed to be a square. I just realized I wrote cubes down here. I'm so sorry about that. Those are both squares. So plus b squared here, well, b is a 3, and 3 times 3 is a 9. This is our solution. Moving on to our next example, this is a difference of cubes. We have two terms. we have a minus sign in between, and they are both perfect cubes. 2x times 2x times 2x is 8x cubed, and 1 times 1 times 1 is 1 here. So the difference of cubes formula is going to factor to a minus b, a squared plus ab plus b squared. So when we factor this, starting with a minus b, that means 2x minus the 1. Then we have our trinomial, so take a squared. 2x times 2x is 4x squared. Plus a times b. 2x times 1 is just 2x. Plus b squared. Again, b squared, 1 times 1 is a 1. And this is our difference of cubes problem factored out.